Okay, so in this video and example, we'll be going over free body diagrams and how to apply and use them in an example. So objectives with this question are to understand how to draw and apply free body diagrams and how to understand supports and equations of equilibrium. So for some quick review, free body diagrams. Here are the steps on how to properly design one. First, you need to establish a coordinate system. Second, you need to determine what you were studying, what part are you focusing on of the whole. 3, you need to draw all forces acting on that particular body and spot. And 4, you need to write and solve equilibrium equations. So, the equations of equilibrium, these are the sums of the forces in either the horizontal, vertical, or moment directions. So the sum of these, when in equilibrium, will always be equal to 0. So now that we have reviewed these concepts, we can take a look at an example problem. So we have a tree here that leans out of this hillside, and we have 2 vectors of interest acting on it. These 2 forces acting on the tree create reaction forces at point A. And in part A, that is what we are asked to find. We need to find the reactions at the base of the tree trunk to have this tree remain in equilibrium. So in order to do so, we need to figure out what the vertical and horizontal components of the wind component are, as well as the horizontal, vertical, and moment reactions at A. And in part B, we take this a step further, where we are put under specific conditions and need to figure out whether this tree can withstand those conditions. So will the tree stand or fail? So to work through this problem, we first need to draw a free body diagram. And keep in mind that the directions shown here will always be positive. So this singular black line can represent our tree, and I've provided some dimensions to make things more clear of where the forces are acting. And we have our point of interest, point A, at the base. So we're first going to start with vector G, which is 10,000 pounds downward. So we'll draw that. Next, we'll look at the 4,000 pounds of vector W. And it's important to note here, as shown in the other diagram, that this is at an angle of 20 degrees. So now, we need to break down and show what we are actually interested in solving for. So for vector W, we want both the vertical component and the horizontal component, in this case shown by WY and WX. I've chosen these directions because they make sense with the vector W. The vector W is going upwards and to the left, so it makes sense that the vertical component would be upwards and the horizontal component would be left. The reactions at base A, I'm going to simply choose to make these all positive convention, as shown by our global axis. You can choose to depict these however you want, but for the sake of simplicity, I'm choosing to represent them as positive. So AY is upwards, AX is to the right, and moment A is counterclockwise. So now that we've gone over this problem and broken it down into a free body diagram, take a moment to see if you can solve these on your own, and then come back to this video. So in part A, we're first going to look at the vertical component of the wind force, which we established as WY. So WY we can find by taking a look at W and using the angle of 20 degrees. So WY is equal to W times either cosine or sine 20 degrees. And how we know that it is sine 20 degrees in this case is because WY is on the opposite side of where the angle is located. So we use sine 20 degrees in this case. So now we input 4,000 pounds, multiply that by sine 20 degrees, and you'll get 1,368 pounds as your solution. making this the correct answer. Now on to the next part. We're looking at the horizontal component of W, which we labeled WX. So again, taking a look at W and using the angle of 20 degrees, but this time WX is on the same side as the 20 degrees. So we know that WX will be equal to W times, in this case, cosine 20 because they're on the same side. Now we also need to remember to include this negative because WX is going against the sign convention we have set for ourselves. So WX is equal to negative 4,000 pounds times cos 20 degrees. So WX is equal to negative 3,759 pounds, making this the correct answer. So we're now moving on to our reactions at A. So here we have listed previously our WY and WX components. We're now looking for the horizontal reaction at A, which we have labeled AX. So we'll find these reactions by using equilibrium equations, in this case, in the horizontal direction. And in order to maintain equilibrium, they have to be equal to 0. So 0 is equal to the sum of all the horizontal forces. So in this case, AX, which we have established is positive, minus, because WX is going the other way, the absolute value of WX. Now what's important to note here is that you have to be careful with your directions when writing your equilibrium equations. You don't want to accidentally put the negative twice. You need to make sure that you're only inputting the negative once so you don't end up accidentally canceling something out. I prefer to use absolute values and simply put the directions as the functions of what we're doing. But there are other ways you could do it as well. You can consider the directions at the end, and you can add everything and just make sure you input the negatives in the actual equations. You just have to be really careful and make sure you're not overdoing it. So rearranging this equation, we get that AX is equal to the absolute value of WX, meaning that AX is simply equal to 3,759 pounds. Making this the correct option. Now we're going to take a look at the vertical reaction at A, which we've labeled AY. So we've already established we're using equilibrium equations, but this time we're going to be adding up all the forces in the vertical direction, which will include G. So we have AY, and we have the absolute value of WY, which is upwards, that's why we're adding it, and minus the absolute value of G, it is downwards, which is why we are subtracting it. We rearrange this equation, and we get that the absolute value of G minus the absolute value of WY is equal to AY. So AY is equal to 10,000 pounds minus 1,368 pounds. So AY is equal to 8,632 pounds, making this the correct answer. And finally, for part A, we're going to look at the moment reaction at A, which we've labeled MA. So we are once again using equations of equilibrium, which we know is equal to 0. So MA is positive convention in this case. Now we need to figure out what directions of moment all of the other forces cause on point A. So for the vector G, this causes a counterclockwise moment as it pulls downwards, as shown below. So that means it is positive. So we will add the absolute value of G multiplied by the perpendicular length, which in this case is 15 feet. Then, if we look at WX, it pulls to the left, which will also give us a counterclockwise moment at point A. So it's also positive. So we add the absolute value of Wx multiplied by its perpendicular distance, which is 30 feet. And finally, we'll take a look at Wy. This force will pull upwards, so it'll actually cause a clockwise moment at point A. So it'll be negative. So we subtract the absolute value of Wy times its perpendicular component, in this case, 20 feet. So if we rearrange this equation, we'll get and input all our values. We'll get that the moment at A is equal to negative 10,000 times 15 minus 3,759 times 30 plus 1,368 times 20. And then you'll get all these intermediate values. And finally, you'll get that the moment at A is equal to negative 235,410 pounds per feet. But you'll notice that's not an option here. So it's important to note that in the question, we're asked to round our answer to 4 significant digits. So our actual answer is equal to negative 235,400 pounds per feet, making this the correct answer. And finally, for part B, we are given these maximum reaction forces that the root system of the tree can produce. We need to find out whether the tree will stand or fail. So, for the tree to stand, these conditions must be true. Our reactions that we found must be less than all of the maximum reactions we are given in the question for the tree to be able to stand. So, since this is true, and this is true, and finally, so is this, we can therefore say that the tree will stand. In summary, these are all the questions and their respective answers. Thank you for watching this video.